It says, an aircraft is flying horizontally and parallel to the plane of the ground. Plane is flying with a constant velocity of 3 times 10 to the 2, which is 300 meters per second in the positive I direction. It's going to drop a package from 2,400 meters above ground. We want to see how long it'll take for this package to hit the ground. So, classic physics question, and what you want is you just want constant velocity in the horizontal direction and accelerating in the y direction. So it's just about breaking them up into two separate motion considerations. Alright, so how long will it take for this package to hit ground? You just analyze the y dimension for that. Delta y equals 1/2 ayt squared plus viyt. So for my delta y, I got to plug in what the package is going to do. The package is going to go down, and that's going to be the delta y. So I need the delta y to be negative. Alright, so when you plug it in, you want negative 2,400 as the distance it travels. And then for your a, you want negative 9.8. Gotta always consider the directions with these. And then when it comes to the VIY, sometimes people get confused on this one. They might put in the 300. It's a classic mistake though. Okay, because the 300 is in the horizontal dimension. But this calculation is not for the horizontal, it's for the vertical. So you got to know that any vector that points in the positive I direction is not pointing in the j direction, which means that this needs to be a 0. And then you just solve for t. Looks like it's going to hit after 22.1 seconds. Now it'll ask how far does the package travel horizontally after its initial release. So for that, we switch over to the x dimension. And you could use that for constant velocity. Alright, so delta x, we got to plug in our speed in the horizontal direction and our time. (6630 meters). So we want to come up with a vector form for the position of the object. Alright, now you can assume that the origin is the point directly below where the package was released. So it's like you're setting up a coordinate system right here. Alright, now that's our plus x, this is our plus y. When you do that, you can create what are called position vectors, but two-dimensional position vectors. And what these do is they point to where the particle is located relative to the origin. Alright, they are called R vectors. So it's not x and it's not y because it's a combination of both. Alright, so how would we do that? Well, we have to start by setting up where does t equals 0 happen. Over here this is going to be t equals 22.1. Alright, now we know that the thing is moving with constant velocity in the horizontal. So it might be easiest in all reality to start with the acceleration, the second derivative function. Now, when it comes to acceleration in free fall, it always points one way, as long as there's no air resistance and all that. Acceleration vectors always point down, because that's the way Earth pulls. And it always pulls with the same strength. Doesn't matter whether your particle is high up in the air or low down to the ground. I mean, actually, like, if you're talking about the scale of outer space, it does matter. And that's like part of the future sections, actually. But here near Earth's surface, the difference between the heights is just negligible. So we assume that those acceleration vectors are always going to be like negative 9.8 in the j direction. Negative meaning down. So you could actually just put that in right away, is that the acceleration is constant at negative 9.8 in the j direction. Now what you want to do is you want to build it up to, like, how is the velocity looking? The velocity as a vector will be an integration of the acceleration function. Alright, so what's that going to look like? Well, you have to consider that there are two components, though. Alright, so there's going to be a AX attached to I and an AY attached to J. And you got to integrate both terms separately. So what we're talking about then is an integration of 0I minus 9.8 J. 0 because there's no acceleration in the horizontal dimension. Earth doesn't pull to the left or right, is the idea. When you integrate that, though, you get a constant Vix, it would be called, attached to I. And over here, you'd get negative 9.8, and then, but times t. And you could have, potentially, some constant as well. Alright, that's the way to write that, so that you have a constant times your I, so constant velocity in the horizontal, and here you have a potentially changing velocity for the y dimension. Hope that makes sense. So what are those constants? You have to go back to the situation to find them. And this is just one, a little bit advanced way of writing it. It may look a little scary like at first. And you can write it differently, and I'll show you like an alternative way to write it, like if that is scary. What you'd want is to just, instead of keeping it as a vector with I and j separate, you could just work with this. You've got a certain ax, and you have a certain ay. And we know that ax is 0. There's no acceleration for this plane to the right and left, because it's not speeding up, it's just constant 300, right? But your AY would be negative 9.8. That way you don't have to deal with the I and J's at all. And so then what you do is just say, okay, Vx will be the antiderivative of AX, and Vy will be the antiderivative of AY. It's just that what I wrote below is a concise way of keeping it all together in one line. Basically what it comes down to is this is the I and this is the J. But I'm going to do the same kind of thing, just keeping them separate, you know. So for this one, I would do integral of 0 dt, and for this one, I would do the integral of negative 9.8 dt. And so Vx here comes out constant, c, and then this one, Vy, comes out to negative 9.8 t plus some other constant. So the constant to use for this problem would be 300. That was the speed in the horizontal dimension. The initial speed, like you could, instead of writing C1, you could write like VIX. And then instead of C2, you put VIY. But the VIY is actually 0 because it wasn't moving up nor down when we first started. So this would be the final formula for how the velocity is changing in the y dimension, and then here the velocity in the x dimension is constant. So now you just put them together and you say v as a vector is going to be equal to 300I minus 9.8t times j. Alright, so that is what to put here. Alright, so then we need the position. So we just want to integrate one more time. Alright, so our r of t will be an antiderivative of v of t. Alright, so we need an antiderivative of 300I minus 9.8 tj dt. Alright, so just like I did before, just treat them as if they're separate integrals. You know, and what would you do? You'd 300t plus some initial x position. That's for the left side there. And then we attach that with I. Then over here we'll get, let's put the 1/2 in there, 1/2 9.8 t squared plus yi. Alright, if you do them all in one line, that's what you get. But if you want to just do them separately, you could totally do that. You could say once again that, okay, we've got Vx equals 300, and we've got Vy equals negative 9.8 t. So now we integrate to find x, which is the antiderivative of Vx. So it's going to be the antiderivative of 300. And then y will be the antiderivative of Vy. Alright, so what do you get in the end? You get x is 300t plus xi, some initial position. And then here you get y equals 1/2 9.8 t squared plus yi. So two totally separate ways of doing it, but they say the same thing. Alright, you'll just want 300t here attached to I, and then over here you want minus 4.9 t squared plus 2400, and that's attached with j. It's supposed to be a negative on there. Yeah. Alright, now we want to see, like, does this really make the graph that is shown there? And you could do that with Desmos, because Desmos has what's called a parametric plotter. What parametric means is that you have separate equations for x and y. but they are in terms of t. So let me write those final equations here, and then we'll plot them with Desmos just to confirm that we did it right. So here we'll have x equals 300 t plus 0, basically, is what it is. So we don't need any initial position. That's because it starts being above the origin. And over here we'd have y equals negative 4.9 t squared plus 2400. Alright, let me bring up the plotter. Alright, if you just do a Google search for Desmos parametric plotter, you'll find it. And you may not even really have to go to that. You could probably just go to Desmos alone. But the idea is you want to type in your formula a little different because this is a two-dimensional type of thing now. So this is just the component form, it's called. So like here's an example, t comma 4. We don't need that. So all it is as time goes up, your object moves to the right as time goes up, but the vertical component just stays a 4. Now you could change your range of t. Better go from negative 10 to 10. Okay. There we go. Now our graph is a little different. You want to put in what you said the x component was, 300t. You can see how it holds a constant vertical value though, and our function doesn't do that. Our function is negative 4.9t squared plus 2400, I guess, so I'm probably gonna have to zoom way out. And check it out. That is the path of a dropped projectile. Starts up high when the plane releases it. It starts really at time 0. That's when it's dropped, though, you know. Alright, then I better let the time go a little farther because we said it would hit ground at 22 seconds, right? So let's go to like 22 seconds. And you can see the entire flight of that projectile because we described it using a two-dimensional position vector, basically. You can see like the 300t tells it to move forward, you know, like horizontally. This part tells it to accelerate downward toward ground and start off at an initial 2400. Alright, so how do you find the speed rather than the velocity? So velocity is a vector, which means that it can have more than one component to its motion. There can be an x component, y component, z, and all that. But speed is not a vector. Speed is just a size of something. In this case, it talks about how much distance it travels in time. So the notation for velocity is different than speed, especially when you're talking about 2 dimensions and 3 dimensions. Velocity will have a vector over its head. Speed won't. You could just see that. There are other ways to write speed though. One way would be that it is the magnitude, it's called, of the velocity. These mean the same thing. Sometimes I write it with a little subscript s just to make it clear to a reader that we're talking about the speed. Alright, so we have a formula for the velocity of this falling projectile. We want this and this. Alright, so we're going to have 300 comma negative 9.8t. Plug those things into the formula. Alright, let's plot that, which would be 300 squared. That's 9.8t squared. Okay, that's good. Now what this is showing is the speed. It's just a scalar number. That's all it is. Not a vector. You can see where it starts. It starts at 300. And that was the speed of the plane, and the projectile's in the plane, so the projectile and the plane have the same speed to start. But as the thing falls, its speed increases. That's what this is showing.